If I had been handed this problem on a physics test, I probably would have freaked out. This looks really intimidating, but it's actually not that bad. It's a classic example of a two-lens system. And overall, before we get lost in details here, the overall idea of how we're going to approach this is this. We've got two lenses. This first lens is going to create an image of this object over here. So it creates an image of this object. Then this second lens is going to create an image of that image. And so what we're basically going to do is we're going to use the thin lens formula. We're first going to pretend like this second lens doesn't exist. We're going to figure out what image does this first lens create. Then we'll pretend like the first lens doesn't exist, and we'll treat that image that the first lens creates as if it's the object for the second lens. We'll do another calculation, figure out where this second lens creates an image of the thing it thinks is the object, but it's actually the image from the first one. And so we're going to figure out first the object gets turned into an image from the first lens, then the second lens turns that image into another image, and that's what our eye is going to see. So that's the question we want to answer is what image would our eye see in this case if we had it over here looking through these two lenses? So let's do this. First thing we got to do. So I'm going to pretend like the second lens doesn't exist so it doesn't confuse me. We use the thin lens equation. All right, here we go. 1 over f. So 1 over, okay, here we go. 12 centimeters. Do I make it positive or negative? It's on the left. Maybe I make it negative. Nope. The only thing you look at is what kind of lens this is. This is a convex lens. I can tell by the way it's drawn. Since this is a convex lens, my focal length is going to be positive 12 centimeters. So that's what I plug in. Positive 12 centimeters equals, all right, object distance. So 1 over the object distance, that's 24, right? No, all distances are measured from the center of the lens to the thing you're looking at. And so for an object distance, I'd have to go from the center of the lens all the way to the object. Don't just plug in any number they're giving you. Got to plug in that distance, and that's going to be 24 plus 12. It's actually 36. So I'd have 1 over, and this is going to be 36 centimeters, positive or negative. Well, that's going to be positive here. We've got two lenses, but for this first case, it's on the left-hand side. Everything's cool. It's on the opposite side as my eye. It's going to be a positive 36. I'll show you in a minute how this could possibly be negative in a second. Plus 1 over the image distance. I'll just label that with a DI. All right, so now we just got to solve. If you solve this, you're going to get 1 over 12 centimeters minus 1 over 36 centimeters equals 1 over DI. What you're going to end up getting is 1 over 18 centimeters on the left-hand side equals 1 over DI, but that's 1 over DI. If you solve that for DI, you'll get that DI equals 18 centimeters, positive 18 centimeters. And so what does that mean? Where is this? Well, all right, DI, positive image distance. Remember, positive means on the same side as your eye for a lens. So I'm going to have an image that's formed over on this side of the lens, and 18 means 18 centimeters from where? From the center of the lens. So if I draw this, I'm going to go 18 from here. That's going to be past the focal point because I know the focal point's only 12, so I'm going to be somewhere around here. I'm going to label that. That's going to be 18 centimeters. And that's where the first image is. So that's where the image is going to be that this first lens creates. It's going to be right there. Okay, so now what do? I told you. Here's what we do. We pretend. We'll bring the second lens back. We know the image that the first lens created is right here. This second lens is going to think that that's the object. It's going to create an image of that image as if that were an object. So we do another thin lens formula, but this time we treat this positive 18 not as if it's the image. We treat it like it's the object. So this is going to be, well, it's not going to be exactly equal to DO, because remember, you have to measure everything from where? From the center of the lens. So for this second calculation, my object distance is going to be from the center of the lens all the way to, let me not use that color. Let me see. Let's pick this one here. From the center of the lens all the way to where the its object is, and its object is over here, which is not 18. That's why I gave you this distance between lenses. The distance between lenses is 33 centimeters. So if the distance from this first lens is 18, well, the difference has to be equal to this length. So 33 minus 18 is going to be 15 centimeters will be where the object, quote unquote, for this second lens is going to be. So we turn this positive 18 into object distance of positive 15 centimeters. Why positive? Well, it's still on this left-hand side, opposite side as your eye. That's where the objects are supposed to be. Now here, this is where I told you there's one case where you can get negative object distances if our first lens would have created an image of this object way over here on the wrong side of the lens. In other words, if this first lens created an image that was closer to our eye than the second lens was, well, that's just all messed up. That's going to be a negative object distance. You're not supposed to hold an object between your eye and the lens. So we'd count that. You'd do your calculation just the same. I mean, everything would work out right. It's not like the whole thing's going to break. You'd get an image. It's just when you do your calculation for this second case, if your image ended up on the wrong side of the lens for the first image that was created, you'd have to treat it as a negative object distance. That didn't happen here. Our image is still formed on this side. We're going to pretend, like this first lens didn't exist. We got an object over here. We're going to treat it like our object. Everything's fine. Eye looking through the lens at our object, so we still treat this as a positive 15. So let's do our calculation. We'll have for this lens, it's going to be 1 over, all right, focal length. What do we look at for focal length? We look at what type of lens this is. This lens is a diverging lens. Diverging lenses always have a negative focal length that they contribute into this equation. So a negative 10 centimeters. That's the focal length of the second lens. Equals 1 over our object distance we just found. It's not really an object. That's okay. It's an image, but this lens doesn't know that. It thinks it's an object. So 1 over positive 15, because it's still on the side that object was supposed to be on, plus 1 over our image. This is going to be a second image. This is the second image that this lens system is going to create, and so I'll just put DI. All right, so we do the math. All right, 1 over negative 10 centimeters minus 1 over 15 centimeters equals 1 over DI. You solve that on the left-hand side. You flip it over, you're going to end up getting that DI is, once you do that inversion, negative 6 centimeters. That's what our second image is going to be. So what does this mean? Negative 6 centimeters. This is always from the lens, and negative, remember, negative image distance means on the left-hand side or the opposite side as your eye. So I'm going to come up here and I'm going to draw a line that goes from the center of my lens 6 centimeters to the left, somewhere around there. That's going to be 6 centimeters right here. Whoops. I'll label that. That's going to be 6 centimeters because that's our image distance. And that means our final image is right there. Our eye is going to see an image of something, our arrow, right at that spot right there. That's where our image is going to be. And just to recap what happened. Whoops. So this first lens created an image of the object over at this point here, this 15 centimeter point. And then the second lens created an image of that image. It treated it like it was an object. And it created an image at this white point right here. That's where we're going to see the image. But we don't know what it's going to look like. These calculations, this thin lens formula only shows us where the image is going to be. If we wanted to figure out how big it was, we have to use the magnification formula. So let's do that. Over here, magnification equals negative DI. Remember, it's negative DI over DO. All right, so what was DI for this first case? We're going to do it one step at a time. For this first case, the DI was positive 18. So I'm going to put positive 18 up here. I'm going to leave off the units because they're going to cancel. DO was not 24, it was 36. So what do I get? I get negative 18 over 36, that's 1/2, negative 1/2. What does that mean? That means this first lens, the image it created, is going to be an image that's 1/2 as big as my object, and it's going to be negative magnification. That means it's upside down. So I'm going to draw this first image. I'm going to do it in orange because that's what I labeled the image distance. It's going to be upside down and half as big as the object. So if the object was that big, my image is going to be upside down and about half as big. So this was my image 1. I'll label it image 1. That's what I'm treating as my second object. So that's image 1, that's object 2, essentially, because that's what this second lens is going to think is the object. What magnification does it provide? Well, let's do that one. Magnification equals negative di over do. So negative of my image distance for this second lens was negative 6. Remember right here, that's what we solved. The second lens created an image distance, negative 6. I'll leave off the units because they cancel. And my object distance for the second lens was 15 centimeters. That was what this was right here. The distance from the lens to where its object, quote unquote object, was. And that was 15, positive 15. And what do I get? If you take negative of negative 6 over 15, you end up getting positive 2/5. So this is the second magnification. The magnification of the first lens was negative 1/2. Magnification of the second lens was positive 2/5. That means at this point over here, I'll make it white because that's where I labeled this image distance. I'm going to get an image that's 2/5 as big as what? As the first image. So now this is a magnification of the image because that's what this second lens is doing. So I don't look back at my object over here. I'm done with this guy for now. Now I'm just looking at what this second lens thinks is the object. So 2/5 as big as this object, and positive means right side up. But in this case, this really just means not inverted. So this started off, our object for this second lens started off upside down. This positive means that you maintain the direction. You don't invert it. So I leave this thing upside down. That's what it means. I leave it upside down. If it would have started right side up, I would have left it right side up. But in this case, I leave it upside down and I make it 2/5 as big. 2/5 is a little under 1/2, and so I'm going to draw this about like that. That's where my image would be, right there. That's what I would see. I would see a very little image that's upside down, and it'd be right around there. And so that's an example of where you can do a two-lens system. You treat each lens separately, and you use these formulas accordingly. The last thing I'll say is if you wanted to know, well, we had two magnifications here. Is there some way to figure out the total magnification? Some slick way of doing it? Yeah, and it's really easy, it turns out. You can just take your total magnification. If all I wanted to know was if I had this object, what my total magnification was going to be. What could I multiply this object's height by, in other words? What factor could I multiply it by to get the both orientation and height of this final image? Well, you just take the magnification of the first lens times the magnification of the second lens. If I had more, I'd just multiply them all. That would give me the factor. That's the overall magnification that I could multiply this object's height by to get the height of the final image and the orientation of it. It doesn't give you the position. This just gives you the overall magnification. That can be handy if you're making a microscope or something. But it doesn't tell you the position. For the position, you've got to use these thin lens formulas. So that's how you treat a multiple lens problem.